Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
He's going to talk to us today about some very interesting tracking multiple people with multiple cameras. It's a very impressive demonstration. Very interesting.
Thank you. Okay, it's a pleasure to be here today. So the project I'm going to talk about is a multi-camera tracking system we developed at so it's a CV lab, which is a laboratory about which we're doing computer vision at EPFL. This work was done initially with Richard Lengagne, who is now working with a company we were collaborating with for this project. Pascal Fua is the head of the CV lab. And Jérôme Berclaz is a PhD student. He started his PhD last summer. So the first part of the talk, I will insist on some first part of the algorithm, which was done mainly with Richard, and the second part, which involved the Hidden Markov models and other things, is more the work of Jérôme. So typically what we try to solve is this kind of we are dealing with this kind of video. So you have a scene, which is a scene from multiple cameras. People are walking by, so typically it's a metro or a hall or a place where a lot of people pass. And what you want to do is to estimate how many people there are in the scene, where they are, and hopefully you'd like to have a confident score, which is not only to say, okay, there is some guy here, but more like there is probably somebody here, but not so sure. So the applications, okay, so this is the kind of things which are of interest for many people, typically preprocessing for behavioral studies, so being able to have long sequences of some, let's say, stadium or things like that, and to be able to locate people precisely and to give information like what is the area they like to have around them when they walk around, and maybe to be able to build models to predict what happens when there is panic and stuff like that. Hazardous area control, which is to be able, for instance, to stop a metro when somebody is really close to the way. People counting, so in public places, museums, things like that, and of course surveillance in the police sense, like being able to say in an airport, for instance, okay, some guy has been staying at this precise location for like 5 minutes, something weird is happening, we should check. This is normal. Okay, there have been like zillions of papers on this kind of subject. Mainly there have been monocular techniques, which would have only one camera filming the scene. Okay, I won't go into details, but a lot of them are based on color histogram, HMM, so hidden Markov model. You have a hidden state which allow you to put the consistency for the motion. And then, yeah, there are optimization schemes like MCMC and representations with particles. Some of them involve boosting steps to reinitialize the algorithm to avoid. And then there are other works in multi-view. Okay, again, a lot of things have been done. We were originally mostly motivated by the work by Metal and Davis, the M2 tracker. Typically, in that case, because you have multi-view, you would work either in both views separately, or you would try to work in the top view, which is what we are going to do here, and to estimate where are people on the ground, and from this to use the consistency between views because your cameras are calibrated. Okay, so the first part of my talk is this probabilistic occupancy grid. It's really like we are going to process one frame, one isolated time frame, and try to guess where people are located with some confidence score. Then the second part, I will show how you can use this information in a more complete model, which involves HMM and dynamic programming to optimize trajectories. So in this first part, the goal is to compute in isolated time frame, so we don't have any more a motion model. We can't rely on the fact that people from one frame to the other have consistent motion. We want to estimate in each isolated time frame, and for every location in the scene of interest, the probability of occupancy according to the result of a background subtraction algorithm. Why are we working on this specific problem? It's because initially this project was a collaboration with a company called VisioWave, which sell surveillance systems, multiple camera surveillance systems. And they had this background subtraction algorithm, and in many situations they wanted to process only this information because it was the only information remaining on transmitted on the network of the surveillance cameras. So when I say background subtraction, this is their algorithm, so which is extremely fast. This algorithm was written like 4 or 5 years ago. It was able to process something like 16 streams on one PC. So it's not so great. Some other algorithm can do a better job, but this one is extremely fast, even on a basic PC, which was 5 years ago. So typically, I don't know if you're familiar with background subtraction. Typically, at the same time, you estimate a kind of a background image with a sliding window, averaging on a sliding window, and you estimate what pixels differ from this background image, and then you have thresholding. In this case, more than thresholding, they are also doing post-processing to remove isolated points and stuff like that. So at the end, the signal we have access in this first part of the algorithm is only this. And as you can see, many times they miss the legs or the heads. You have false positives, holes everywhere. You can't really rely, for instance, on a precise silhouette matching. Okay?
It seems like it comes in little blobs.
Yeah.
The blobness?
I think the blobness comes from the fact that they post-process with a classical artificial vision algorithm, like you remove isolated points and then you do growing, whatever. Okay, the idea is that for what we are doing, I guess we would have preferred something far less processed, like a raw pixels probability to be background, like Liud score, something like that. Okay, so the goal of this first part would be to work on isolated temporal frames, to combine several views, of course, to provide a probabilistic estimate, which is not to work in the kind of a geometrical spirit, but really more probabilistic framework, like, okay, there is probably some guy here, or maybe some guy here. To handle very noisy blobs, as we have seen, they are not so great. To take into account blob size for distance. What I mean by this is that even in a monocular situation, you want to be able to say the guy is probably at this distance. You don't want to rely. Of course, if you have multi-view, you do some kind of triangulation, and you're able to localize the guy pretty accurately. But if you have only one view, you can still do something. And also, we want to handle occlusions consistently. This is more like a constraint in terms of intellectual consistency. For instance, I guess we agree that if the algorithm is inconsistent, if I'm sure there is a guy at a certain location, if my estimate of the probability of presence is like 0.99, it would be crazy to say that at a hidden location, I have a location which is hidden by this guy, I have another estimate than the prior. If my estimate tells me that I'm hiding a location, this hidden one, my estimate should be the prior, because by definition, I don't have any information about it because somebody is hiding it. Okay, so we first start by discretizing the scene of interest, which means that we divide the ground into a regular grid of roughly 1,000 locations, which correspond to a 20 centimeter accuracy. It depends, because I have several sequences, it goes from 20 to 30, but keep this figure in mind, it's like 20. So typically, I will have pictures like this in the talk in different slides. Each time we have the views from the cameras, the grid on the ground, on the top view. So this is the top view, and you see the field of views of the first camera, which is this part, and the field of view of the second camera, and you have a correspondence. Each point here corresponds to a point here. We also have the camera calibration, which means that we have the mathematical transformation between the image field into the ground. So we can go from a point on the ground into the every image field. And from this, what we build, and then we will forget the camera calibration, if it works. From this calibration, we build a collection of human shapes, between quotes, because it's just rectangles. But rectangles allow us to do a kind of algorithmic optimization at the end. So here what I show is the top view, and for each location on the ground, I show the corresponding human shape. Human shape in the sense that it's 175 centimeters high, 30 centimeters width. Okay. Okay, so now my notations is this K, C is the rectangle standing at location K on the ground in the camera C field of view. Okay. Now I introduce the following random variables. One is xi, which stands for Boolean random variables, which stands for the occupancy of locations. So for every one of those discrete locations, I have one Boolean random variable, which is equal to 1 if there is somebody, 0 if there is nobody. And I denote by B the produce of the background subtractions. The background subtraction. So those are random variables on this, which are typically binary images of size WH. So BC sorry, is a binary image produced by camera C by the background subtraction, and XK is the presence of somebody at location K. Okay? In an ideal world, we would be able to compute this stuff, and this is what at the end the algorithm will produce. The posterior of the distribution of people, knowing the result of the background subtraction. In practice, this is an extremely complex distribution. Even if you have a simple prior, which is what we have, when you condition on a certain background subtraction image, it makes some pretty bad dependency. Because, for instance, if I tell you there is a blob somewhere, and there are two rectangles that could explain this blob, and now I tell you, oh, this guy is not here, you're sure the other guy is there. So it creates dependence between people, even if the prior is independent. So we make the following independence assumptions, which is that first the xk's are independent, which means that before I look at the pictures, it's really like I have flipped a coin at every location and put guys each time. Okay, a coin is not probability 0.5, but I have probability epsilon to have a guy at each location, and they don't look at each other. This is not true because this is true. This is not true for if you want a detailed representation, because if you take a picture of a metro hall, for instance, people try to have a kind of a space around them. So even before you look at the image, you know that if you have somebody at some place, there is some kind of empty space around it. We ignore this second effect. And also, we make the assumption that the images produced by the background subtraction, given the occupancy, are independent. This is slightly more subtle. It means that, of course, the images produced by the background subtraction are not independent. If I show you one image, the background subtraction produced for camera 1, and you see a big blob at the center of the scene, you know that you are likely to have a blob on the image produced by another camera. But this dependency due to the actual presence of people. If now I tell you where the people are, I tell you there is a guy here, a guy here, a guy here, nobody else, and now look at this picture, you will see the blobs you were expecting to see plus some noise. That does not give you any clue about the noise on the other view. So this is true when we think about it like this. This is not true when we start to think about second order effects like morphology, clothes, hats, whatever. If I tell you there is a guy here, and now looking at the blob you realize that the guy is Michael Jordan, it's like 3 meters tall, it gives you information on the second view. Okay, we ignore this. We make the assumption that all the correlations, the statistical dependency between views is due to the presence of people. So, okay, it gives you those two assumptions. The fact that the prior is a product law, and the fact that given the occupancy, so the law of the cameras of the binary images is also a product law. What we can do with our collection of shapes is a kind of a crude synthesis. If we knew the xi, we could put it, each time we have a xi equal to 1, we put a rectangle. So typically for those xi's, you would obtain those synthetic images. Okay? From this crude synthesis, we are going to model the probability, the distribution of the images produced by the background subtraction given the actual occupancy of the ground. And this model is just that we have a kind of a pseudo distance, which is a L2 norm between the images produced by the background subtraction and this ideal image, ideal synthetic image, divided by the norm of the ideal synthetic image. Why is this weird asymmetric distance? Because when you look at the image, you realize that the background subtraction algorithm has a noise which is proportional to the surface of the true image, which it's more like it scrambles the pixel more than adding a pixel noise everywhere. So this term takes this into account. And now we model the distribution of the background subtraction images given the true occupancy of the ground. This is our assumption of conditional independence, so it's the product over all the views given the true occupancy. And we make the assumption that this has this following form, which is exponential minus the distance between the two images. To make it short, probability to produce a certain image by the background subtraction is just the product over all views of something which goes down with the distance between what produces background subtraction on the true ideal synthetic image. Okay. Because we can't really represent this, it's too complex, we are going to try to approximate it with a product law. So I denote Q, this product law. So it has the following form. And we are going to look for marginals. So if I give you all the QK, which is the probability of presence at every location, this law is not completely known because it's a product law. And I want to find the QKs so that Q, the big Q, look like P given B. So I want to find what marginals of product law so that it looks like the posterior distribution given product of the background subtraction. So the way to go is to try to minimize the Kullback Leibler divergence. So the Kullback Leibler, I don't know if you're familiar with this, you can see it roughly as a distance between distributions. It has really nice properties both from a theoretical perspective and really from a pragmatic perspective, because when you write the math, often some miracle happens, terms cancel. So basically what we are looking for is the QKs so that the Kullback Leibler divergence is optimal, which is that now we are going to look for the QK so that this differential is equal to 0. I denote by big E of big Q the expectation when X follows the low Q. So this symbol just means it's like averaging a quantity by generating zillions of samples with my by flipping a coins independently according to the small Qs. When I do this, I just average by generating X's independently according to the Q. If we minimize this, we obtain this expression, which means that small q of k equal 1 over 1 plus exponential of a prior, which is the prior, it's the log ratio of the prior, of the expectation of the log of these things minus the log of these things. I will come to it later. Yeah, sorry.
So is your approach very much like the maximum?
I don't.
You have first you have the constraint.
Yeah.
Basically your constraint is you want to minimize the sort of well, first of all, the constraint is you want to minimize the pseudo distance.
Okay.
Between what you observe, B is what
you
observe, and A is synthesized, generated by you know the state and you want to
I haven't thought about it like this, but maybe. So it would be like finding the low Q, which maximizes entropy, and still the low of A would look like B.
Yeah, because
I agree.
If you have the constraint and you write down the maximum entropy, it's just something like minimize the error distance.
Okay. Okay, maybe. But actually, I'm not. I don't know so well this maximum entropy things, but. Okay, it's like maximizing entropy so that the law of a mapping looks like the law of a law, okay. Maybe. It may be. It may
just say, for instance, you don't have any information, the constraint is uniform. Fine.
Yeah.
If you have it.
Yeah. Okay, maybe.
So you're going to talk more about this equation?
Yeah.
Okay, good.
Do you think it's a good idea? Yeah.
Yeah, no, I would like to.
Okay. So the proof. So you want to make this 0. We agree. So this is true by definition of the Kullback Leibler.
Back to the motivation as well. So here, we
One more slide back. Yeah.
So the probability of X, which is the occupancy,
Yeah.
given the observation,
Yeah.
is intractable.
Yeah. Because typically you would need to average under the conditional distribution of X given B on this history bar. So you do the opposite. You are going to...
Actually, but I'm sure you're right here, but just for my intuition. So so we know how to compute the probability distribution of B given X, right? That's just you render.
Exactly.
Right. But here we want to do the X given B. What would you have to marginalize it for? Why would that be? Just to say it again.
No, well, you would have to average under the conditional law. So you would have to marginalize all the x's. If you want to compute probability of xk given b, you would have to average letting all the other x. Numerically, maybe you could. I mean, but now we are going one way. We couldn't numerically generate zillions of samples. It's actually we are doing now something in this spirit. But here we are really processing it analytically instead of sampling. So there is no real way to do it analytically with the. Okay, maybe.
Right.
Yeah.
I think I understand. So now you're saying, well, so instead we want to find something which is going to be of attractive,
Exactly.
which has this kind of product.
Yeah. I'm not such an expert for. Actually, we did this, but there is a whole literature about minimizing this Kullback Leibler so that you end up averaging for the product law. On this, you can do because the product law, it has a more nicer form. Yeah, I guess it's actually it's naive mean field approximation because on the way of linearization at the end, exactly like mean field theory. So it looks like physics stuff. Okay, so I will go through this quickly, but so you want to make this zero. This is the definition of the Kullback Leibler divergence. You average under the first law, the log of the probability according to the first law divided by the probability according to the second law. This is true under our assumptions. This is directly Bayes' law. You replace x given b by p of b, b of x, p of x. This is our model, which is that the q and the p are product laws by definition of q and by assumption on p. This is true because we calculate the differential with respect to qk, so all term which does not depend with qk disappear. So we obtain this form. Okay, now we just condition on xk, so we make the qk appear, and we do this. Okay, this is purely analytical. There is no trick at all. And we obtain something which has this form. So maybe to come back to the equation, it makes a lot of sense. If the fit is better when xk is equal to 1, this is higher. Is it true? I think I mess up. Actually, this should be 0. Okay, but basically this is the fit when xk is equal to 1 on the fit between the image produced by under Q, the image produced for by x, the image A under Q. If it's better when xk is equal to 1 than when xk is equal to 0, the probability goes up, and if it's worse, the probability goes down. It's exactly what you want, the kind of property you want. If when you put the guy, you have an estimate of the qk, the qk's are optimal everywhere, and now you want to recompute the qk at a certain location. If when you put the guy, you force it, you put it with probability 1, and now you generate zillions of samples with the other qk's. If on the average this is better than removing the guy and doing the same, the guy is probably here. So it's exactly what the formula is telling you. But actually I think I invert the two values like half of the time. If it's better when the guy is here, the probability goes up. If it's worse, the probability goes down. Yeah, sorry. This one?
Yeah. So if you look at this equation, so basically, so you're trying to compute two things, right?
Yeah.
And it involves, computing the expectations with
Yeah.
respect to Q.
Yeah.
So
it's a system of equations, actually.
So you do iterative?
Yeah, exactly. Because it's a system of equations. Here, Q does not appear. QK does not appear anymore. All the others QL for L different than K appear, but the QK does not appear. So you really have a system of equations. This is a function of all the QKs, and this is a QK. Okay, but there is still one problem remaining, which is that this still is extremely expensive to compute. So we put it under this form. We know, by definition, we have this because of our model. So you take the log of the priority. I showed that it was exponential of minus psi. So this is under our model. And I do a linearization. So it's really like mean field theory. Instead of computing expectation under Q of psi of the distance, of the distance, I compute the distance of background to the expected. So I kind of do a linearization with respect to the second parameter, which is kind of not so crazy because if you really have the good Q, the optimal Q, you will obtain a law that fluctuates the image A, the big A, under Q, fluctuate around B. It looks like B by definition. So you are just linearizing your psi in this neighborhood of the image B. It's not like you don't expect psi to be linear between two images extremely far away. You just expect it to be linear around. So it's just that it's regular. Okay, now one problem remains, which is can you compute the average image? Okay, we can. The average image if under Q again. If I give you all the QKs and now I ask you what is the expected value of this pixel, what do? You just go through all the QKs that all the rectangles which meet this pixel, look at the corresponding QKs and do a disjunction. So you obtain this kind of expression, which is 1 minus the product of over all rectangles meeting your pixel of 1 minus QK. This is disjunction. Okay? So we have all the pieces of the puzzle. We have a relation between one QK and all the other QKs, and this expression involves an average image that we are able to compute. Finally, to summarize all this, we obtain, after linearization, this expression, and this makes sense. So this is the image produced by the background subtraction. This is the average image under Q of the synthetic image for the same view, given that you put the guy at location K. And if this is big, if this is large, the probability goes down because this is the positive coefficient. So if the distance between the image you actually got on the synthetic image with the guy is bigger than the distance without the guy, the probability goes down. If it's better, the probability goes up. What's interesting that we see that we will have all the properties we expect. One property is going to be that if the guy is far away, the rectangle corresponding to him won't fit the blob as well. So the best ones corresponding to rectangles which fit the blob will be better. So we will have the effect I was talking about. We will be able to localize people. The second property, which is extremely neat, is that now if one QK, so we are going to solve this by iterating typically directly this system. If one probability goes up and goes to 1, all the hidden rectangles will go back to the prior. Why? Because if you have a rectangle with probability 1, which hides the rectangle corresponding to location K, this expression and this expression are going to be exactly the same. If this rectangle is here with probability 1, this other rectangle which is hidden can be here or not here. The average image does not change, which means that those two terms are going to cancel. And if those two terms cancel, the prior remain, and all this expression is the prior, which is exactly what we wanted. If a location is hidden by other locations which are occupied with high confidence, then the probability of those hidden locations will go to the prior. Okay, this is intuitive. This would be the average under Q. This is the same without the guy. We remove this guy. And this is the same with the guys. If this fits better, the probability goes up. If this fits better, the probability goes down. That clear? Okay. The tough part is over. Now it's going to be video. So this is typically what happens. So we initialize all the algorithm with probability like 1 over 10,000, and we run the algorithm, which we recompute everybody with exactly the algorithm I described. And as you see, so the shades of blue stand for the probability, either probability of presence or probability for the pixel to be black. and the greenish stuff is the result of the background subtraction.
Are you assuming you know the number of people?
No. No, we put people and just iterate my algorithm, the ZRC algorithm. And as you see, it's pretty neat. Because the guy has really weird shape, you have some stuff in the monocular area because in this part, so it's slightly spreading around. This one is interesting because one of the guys is visible on only one of the views. I guess it's this guy. I'm not so good at matching picture images. There are guys in the lab doing 3D stuff. They are far better at this. But I think this guy is visible on only one view. And what is happening, sorry, you see that it's concentrating, but still, some part is, this is tough because there is no way by the other view to concentrate. This one clearly, quickly concentrates because if the rectangle was here or here, it would be a problem on this view. This other one, there is no way. But still, the size of the blob gives you a good hint. So it puts this rectangle, the high probability, and the other one still spread around. This was to show how it deals with false positives. So this false positive is inconsistent with the second view. So you keep, your projector is great because even the small shades are visible. This is pretty cool. So here you see that because there is this false positive, it puts some mass, but it's inconsistent with the other view, so the mass has not really increased too much, but still. And also, this is, you will see in the video, at one point they are almost colliding with each other, and still it's able to catch. Okay, there is a bit of luck, because it doesn't really not look like two people, but still, in terms of shape and width. Actually there is no learning in this algorithm. It's really like we are just running the algorithm I described online. Yeah. 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 Yeah.
And I results very sensitive to right?
No, it's flat, and I think we really picked like 1 over 10,000 randomly. Okay, so now I can show a sequence. So I don't know, I still have like 10 minutes or no? Okay. Okay, so those videos are still without time consistency. We are running the algorithm I described, time frame by time frame, and keep the local maximum. We have an ugly heuristic to keep some maximum. And we put a red box at the local maximum. Two cameras, only 2 people. So it's not so. Okay, I can. Okay, this is low resolution. As you can see, we have downscaled the images from 640 to 160. Okay, I will show the same sequences again. Algorithmic complexity, because I feel that some of the questions were wondering how fast this can be. Actually, I can show you a sequence. This is the actual speed on 2.4 gigahertz. This is the actual speed, so 6 frames per second. All this stuff, we have 1,000 equations of 1,000 hidden variables, and we're able to compute it at 6 frames per second. Why? Because there is a trick. You can do a trick with integral images again. You realize that actually, basically, for each iteration, you first compute the average image, and then when you put a guy or you move a guy, it just changes the image in a rectangle. Either it makes this rectangle black, or it divide this rectangle by the probability, the current estimate for this guy. And I won't go into details. We have a technical report, and hopefully we will have a journal paper soon. We give all the algorithmic description. You can organize your computation so that you compute the average image at the beginning of the iteration, and then everything is done at constant time. For every location, you just have a computation of 4 integral images, 1 exponential, and that's it. No, there is not. I don't remember if there is an exponential. Anyway, it's pretty cheap. Yeah? No, in that case, we start with a flat prior at every frame. There is no time consistency at all. Well, we have an extremely dirty criterion, like, now we are entering details, but I think it's something like we run the estimation until it has not fluctuated more than epsilon for more than such iterations. On the average, I guess it's around 100 iterations to converge. Okay. There are the more people you are, the less it converges quickly, actually. So, okay. So, full model. So what I call full model now, of course, if you look at the result carefully, you will realize that there are some extremely bad behaviors, like people teleporting themselves, warping in space, which is crazy. You don't need some sophisticated model to know that people can't jump 5 meters away and come back at the next frame. So now we want to put the full Hidden Markov Model things on color model to be able to change the locations, because so far, with what I've showed, we are not able to follow some guy. We are just able to say where people are in each frame. What we want is to first regularize with the motion consistency, and we want also to be able to say this guy is entering and this is the same guy all along. So we are going to process frames by batches of 100 frames. And I denote now the complete video signal. So it's not only the background subtraction product, but the full video signal with colors and stuff. And I denote by big L of n, bold L of n, all the trajectories of everybody. I won't go into detail, but basically we make the assumption that we have a really large number of people who can be either in the scene or in a hidden location, which is out of the field of view. And all the entrance and departure is dealt with in that way. The fact that each time we are going to compute people already present in the scene and how they can move around, and also people in the hidden locations, they can appear in certain specific location, entrance in the scene, and we process them exactly the same way. So ideally, again, we would like to compute, we would like to maximize this stuff. So the n star being the number of people, trajectories given the full signal, we can decompose this analytically in an exact way under this form, which is it's the probability of the trajectory of the first guy, time probability given the signal, times probability of the second guy, given the signal on the first guy, etc., etc. And so we optimize those terms successively. So we are going to compute the optimal trajectory for the first guy, and then we are going to compute the optimal trajectory for the second guy, given the trajectory of the first guy, etc. The conditioning over trajectories of people we have already processed is just that we can't have two people at the same location at the same time. So we compute the optimal trajectory of the first guy, remove all those locations, and then we compute the optimal trajectory for the second guy, etc. Okay. So it's what I just said. The fact that when you compute the probability of a given trajectory given other ones is just that you exclude those locations for the admissible array. There is something I don't speak about here, is that we have an heuristic. We have a way, really an heuristic to sort the people and to find in which order we are going to process them. Basically, if you process them sequentially, as long as you don't make mistake, so if you process the first person and you find its optimal trajectory and you actually did it right, it will not hurt the estimate of the map for the next trajectories, because you haven't stolen anybody's location. The problem appears if you messed up for one guy, then maybe you will be in trouble for the other ones, because you will have taken the trajectory of somebody else. So the idea is, really practical point is, if you process people and you did not make any mistakes so far, it won't hurt you for the next ones. So what we do is that we rank them according to our confidence in our estimate so far. Typically, if you have a T-shirt like him, red, in this room, we will follow him extremely well because we have the color histogram I will show, etc. So it's likely that this red shirt and this white shirt two blue, this is a problem, but those ones would be followed extremely accurately. So we have an heuristic which rank people according to, okay, the quality of the trajectories in the batches we have processed before. And we process first in the new batch of 100 frames the ones we have followed with high confidence in the preceding batch. By doing this, we have no mistake in the sequences I will show. So we process people one after another, and so we end up with a classical problem, which is that we want to optimize, we want to maximize typically this kind of expression. So a trajectory given the signal. We have the classical recursion, which is that used in the Viterbi algorithm, etc., which is that if you introduce the probability of both the signal and the trajectory, the maximum of the probability of the signal on the trajectory ending at location k at time t, you have the following recursion under Markov model. And you just need a motion model which is pretty to be at a certain location at time t, given that you are at a certain location at t-1, plus an appearance model, probability of the signal, given that the guy is at location k. For the motion model, we use something extremely simple, which is that, okay, basically something going down with a distance and which is cut, which is pruned at a certain maximum distance. So we realize that we call c the maximum distance, which is not that people can go at the speed of light, but it's more like I think it's maybe one square around him, so it's more like 12 miles per hour or something like this. Yeah, I guess. So this is the motion model. And for the appearance model, we show that you can legitimately split it in two parts. One is the color model, which is the probability that the guy is at location k, given that location k, of course, is occupied, and you have the texture at this location. Okay. We call this T of k, which is all the information. This is a bag of pixels. We forget the structure. We just have the pixel with their colors. And we said that we model the probability of the guy to be at location k, given the texture and the fact that k is occupied by this stuff. Basically, it's color histogram. Okay? And this is the estimate of the first part. Occupancy of location k, given the signal. It makes sense, actually. You split into a kind of binary signal without color and a part which contains only the color. Okay, I'm going to be a bit short, actually. Everybody will be happy. So this is typically the results we got. So again, we have a batch of 100 frames. We compute optimal trajectories, one after another. It's 4 cameras, 6 people. We had a carpet because the floor is extremely highly reflective. So it was really bad for the bagging supply chain.
In this case, one is the person you extract first?
Yeah, the first one who entered the scene. Yeah.
But it's not the most, is it the one that's the most identifiable?
No, it's not in what order we proceed. It's really like we follow them. Sorry, say it again.
How do you know the total number of people?
We don't. Sorry. Yeah, it's the entrance on departure. The fact is, virtually it's like if there were 1,000 people in a hidden location, and we make them enter if the map makes them enter. Does it answer your question? No, it's implicit. We had this discussion actually recently at EPFL, but I don't think it's actually thresholding. It's really, imagine that, for instance, you have an hidden location, so somebody is not visible in the scene. And then the signal tells you, okay, something is happening here, but it remains unlikely, it's not clear it's somebody. You have a cost probability to do the jump from the hidden location to the, it costs you have probability only 1 over 1,000 to enter the scene when you are in the hidden location. So unless you have a really clear evidence that there is somebody, it would be more likely that the guy remains in the hidden location than he enters. So the number of people is implicitly dealt with by this algorithm. The fact that if the map tells you that the guy in the hidden location enters the scene, then the guy enters the scene. If the map tells you, okay, maybe there is somebody, but it's so unlikely that somebody enters the scene that he remains, it's more likely that the camera is doing some weird stuff than somebody entering the scene. Yeah?
Did you notice any flickering due to ambiguity? So say if you have two cameras, right?
Yeah.
Kind of looking like this, you get a configuration like this where
Yeah.
The people could be arranged like this,
Yeah.
and it's kind of the same since your background subtraction is quite perfect, you can't use size as well. Do you notice any flickering between like this configuration and that configuration, like the two camera plates? I'm sure there's like an analogous one.
But now you are talking with, when we are working on one frame alone.
Yeah.
Okay, so the first part of the talk.
Then, but this here, we could do the color and everything, then it gets rid of all that.
Yeah, I guess the color and all stuff would, yeah, you would be extremely likely for many successive frames to remain in an ambiguous situation.
If this was a soccer team, though, you might still have that problem, right? Because they don't have the same uniform.
Yeah, we should push for people in soccer teams to have different t-shirts or barcodes. Okay, this is the second sequence. So the first sequence I showed was, people always wonder, the algorithm is not reading, is not predicting what people will do. It's that we have 100 frames, we have a buffer of 100 frames. So what we show here is the first frame of the batch plus the optimal trajectory estimated on those 100 frames that we already have in the buffer. It's not like the algorithm predicts, because many times people were really like throwing eyebrows, thinking, okay, what's going on? And as you see the trajectory, okay, in that case, the grid does not go, does not fill everything. This is a real person. So this is taken in front of one of the buildings of EPFL. The first sequence with 4 cameras was taken with a real high-tech setup provided by VisioWave, where the cameras have a common clock, so it's really highly synchronized. This is taken with 3 cameras, of 2 different brands, and we synchronize the frames afterward by looking at the features. It's just to show that we don't need extremely high-tech stuff. The fact is that this is a nightmare for a computer vision guy, because you have sliding doors, glasses, reflections, people who are moving doors on the chairs inside. You have cars and trains passing by, real people passing in your experiment. On the other hand, we realized that the trajectories we had in our sequences are far more complex than what people are actually doing. If you look at the real people, they actually have a goal. So they walk. There is a first woman who was a yellow trajectory, and you see she's walking straight forward. She's going to the door. And all the real people, when they don't try to be natural and do some natural trajectory, okay, so her, for instance, is not part of the lab. She was just passing by. She's walking straight forward. And then there is another one at some point. Also, we had a problem with the sliding door, because sliding door makes, of course, the background subtraction freak out. He says, okay, there is a big guy. There's a big guy entering the scene. So what we did was to add rectangles in the collection of shapes. Okay, this is also a real person. As you see, she's walking straight forward. What we did was to add some shapes in the collection of rectangles. So we had a big rectangle for the door, and we ran exactly the algorithm the same way. It will just make this probabilities goes up, and it will prevent it from thinking that some people are in the scene. Here it's slightly more complex because the hidden location can make people arrive anywhere in the field of view. In the other scene, there was only one door. We knew that people could enter only on one location. In that case, they can enter everywhere. So it's tough because you can't filter false positive as well. As soon as something appears. Yeah?
So does that mean that you need to calibrate on every environment
Exactly. Yeah. Yeah. We haven't done it. I mean, if you don't do this, it still works. It still works, not as well. So it's more a trade-off between. But what we could even do is to deal with the furniture. Like we would add a rectangle which is here with priority 1 and which deals with occlusion, because it would make. We agree that if you detect a blob here, you will never have a part moving because the part is hidden by the furniture. So you should not put a penalty on people of the because the guy is hidden. You should not reduce the probability. So if you can calibrate with the furniture, you can take this into account. You just put a rectangle with priority 1, and you have the occlusion effect on it works as well. And there is also a result which is on the left. You have the algorithm of the first part of the talk alone. On the right, you have the same filtered by all this stuff with the Markov model and polar histograms and things. But as you can see, this one does a decent job when you have 1, 2, or 3 people, but then it starts to collapse. On this one, of course, this is a bit of cheating because it's a map, so it's perfectly clean. But still.
So on the left, it's like the condition. You're showing this x.
The cues. Yeah.
And on the right, this is actually the trajectory.
Exactly. Yeah.
You
Yeah.
know where these things are.
Yeah, it's the average x. Yeah, it's not the x. It's the average.
Like a video game from 1978.
Yeah, exactly. Is this a compliment?
Yeah, it just has a kind of
I should add music. I should add a Mario music.
yeah, right. Very simple music. Just, not polyphonic.
The problem with this kind of this kind of result, this is extremely neat, but I don't know who is working here with tracking, but tracking has it's pretty pervert, because 99% of the time the results are far better, but 1% of the time it's terrible, because, and we can see it when it starts to fail. You would have, if it starts to believe there is some guy, and by mistake he puts some guy where there is actually nobody, then he's really in deep trouble to remove him, because he has to make him leave by some door. So tracking, when it works well, it's terrific. When it starts to fail, it's...
So your model, if somebody has to disappear, they have to walk off the side? Or are they allowed to just disappear?
No, they are not allowed to disappear. They have to walk. We don't allow ghosts or stuff like that. No, we really compute...
That really matters. That I force people to walk off the edge.
It really matters? No, I guess if you had a priority 1 over 10,000 to just disappear, it would not be such a big deal. Okay, on the last results, what we did, because here, so in those sequences, we don't have any mistake in the sense we never confuse people or miss somebody. But now the question is, what is the metric, or how far are we from the real position? So what we did, okay, it's a pain to go through all the sequence and about everything. So what we did was to take one sequence for which it works pretty well, because it's a 4-people sequence with 4 cameras. So we definitely took one for which it works well. And we picked 100 frames at random, so really uniformly in the sequence, labeled all the people by clicking on the belly, actually, in every field of view, and computed the ground truth from this through the calibration of the camera. And then we computed the distance between our estimate of the location and this ground truth, and we obtained this distribution. So 80% of our detection is around less than 26 centimeters from the true location, which is pretty neat, because the grid, I think on this sequence, the grid is 25 centimeters. So we are exactly in the margins of what we could expect from the discretization. And 90% of the time, it's below 45 centimeters. So it really works, actually. In terms of metric error, it's pretty neat. You see that it's kind of bimodal. I guess we have a really different sort of errors. Those ones are really errors where we don't make mistake. It naturally fluctuates around the good location. Here it's clearly another sort of error where we mess up something and then we correct it. So now we were working with detectors instead of background subtraction. What we did was to produce the ground truth with this algorithm with an extremely fine grid. So because in that case it's really like labeling for another application, there is no issue of computation. We can really run as much as we want. So we increased the grid by a factor 16. So instead of having 1,000, it was 60,000. So resolution like 7 centimeters. And it works amazingly well. It makes nice probability blobs. Okay, future works. Can we make adaptative shapes instead of pure rectangular? Can we have adaptive psi, which is instead of having this ad hoc distance, can we make something that we learn? Can we prove the convergence because we have a fixed point? Do we actually have a fixed point? Can we justify the linearization of psi better? Can we apply this to 3D? It's kind of 3D space carving, like for tumors and stuff like that. Can we improve the visible state instead of having just background subtraction? Can we do something with classifiers? That's what we are working on now. Can we use a sophisticated color model instead of dumb RGB histograms? And can we use a sophisticated motion model, which is maybe one axis we're interested in? Like, you would deal with weird behavior by ringing alarms, and you know that 99% of people, they go to work, they work. So we have two papers. One ICCV in last ICCV in Beijing, which was on the first part. And actually, the algorithm is not presented at all as a Kullback Leibler divergence, which is interesting. Initially, we made the algorithm with another intuitive justification, and it appeared that it was Kullback Leibler divergent. And now we have a paper in CVPR in New York, so it's next month. Yeah, it's in June, about HMM and stuff. Okay, thank you for your attention.